Hello students, in this video we'll discuss curve and flow integrals. If we're given a curve r of t, which we can write as f of t I hat plus g of t j hat plus h of t k hat for some parameter space t between a and b, a less than or equal to t less than or equal to b, we know how to compute the arc length parameter of this vector field. So we know that ds dt, then the arc length derivative, the arc length function s has derivative ds dt is the square root of f prime of t squared plus g prime of t squared plus h prime of t squared. That is our arc length derivative. And so in particular what I can do is I can write the arc length differential in the following way. So the arc length differential is therefore ds is this square root f prime of t squared plus g prime of t squared plus h prime of t squared, all square rooted, dt. That's our arc length differential. This allows me to define the arc length or curve integral. So define a curve integral of the scalar function of f of x, y, z over the curve c as follows. This is the symbol. This is the expression we write, ds. So I'm integrating over the curve ds, the function. And what will this be by definition? So by definition, the integral over c of f of x, y, z ds will be the integral over the parameter space a to b. I input the curve into my function, so everywhere I see an x, I replace it with f of t, little f of t. I replace the y with g of t, and I replace the h with h of t, and then what? And then I do ds, so I plug in this square roots. I have f prime of t squared plus g prime of t squared plus h prime of t squared, square rooted, dt. And this turns this curve integral over here into a one-dimensional a single variable calculus problem. So let's do an example of this. So let's find the integral over c of x squared ds, where c is the unit circle. That's our problem. Now, for this problem, this turns out to be rather nice because we know how to parameterize the unit circle in arc length parameter. So if r of t is equal to cosine of t I hat plus sine of t j hat for t between 0 and 2 pi, then we know that ds is equal to dt here. So then ds is equal to dt. This is a statement that the curve is already an arc length parameter. So this entire square root over here is going to simplify just to 1. Now we can see that because, of course, the derivative of x is negative sine. The derivative of y is cosine. So negative sine squared plus cosine squared is equal to 1. So that whole square root was simplified just to 1 in this problem. And so our curve integral, our integral over c of x squared ds, will be the integral from 0 to 2 pi of x squared. What is x on the curve? On the curve, x is equal to cosine. That's our x. So I do a cosine squared of t, and then I have a what? Then we have a ds, but ds, in our case, is just dt. dt. Now I can use the power reduction formula, the integral from 0 to 2 pi. Cosine squared of t is 1 plus the cosine of 2t over 2 dt. Now, of course, the cosine of 2t averages to 0 between 0 and 2 pi. So when we integrate this, that will give me nothing. That will integrate out to 0. And so we're left with a 1/2 dt from 0 to 2 pi. So this is going to be the integral from 0 to 2 pi of 1/2 dt, and that just is going to integrate to pi. So the curve integral of x squared over the unit circle is equal to pi. Thank you very much.